All right, well, what this is going to do is they are zooming through to show you one of the great superclusters, which there should only be a few tens of thousands of in there, because the people who are doing these simulations really are thrilled by the biggest and most massive things that they see, whereas most of us are impressed by the whole cosmic web that we see what's going on. And so we have the situation where we start with the initial conditions taught to us by the cosmic microwave background observations, and we let ordinary gravity run its course in an expanding universe, and we end up doing this. And this is, since this is going so poorly, let me skip to the next one and show you how a smaller scale version of how the simulation is done. You put in the original fluctuations. They're growing linearly with the expansion factor of the universe. So going from 10 to the minus 5 fluctuations to 10 to the minus 3 to 10 to the minus 2 fluctuations is pretty boring. So we have to wait until, so we go from the universe was 10,000 times smaller, 1,000 times smaller, 100 times smaller, to 30 times smaller. So that number up, 1 plus that number up there is the ratio of the present size to the size of the time the image is. And we'll run the simulation. The fluctuations have grown now by a factor of 1,000, but they're still down at the tiny percent level. It's uniform to a percent. And now let me then just let gravity continue taking its course. And you see things begin to condense, and there's a bit of flow of the galaxies around, and pretty soon you have this network of webs. And right about here, you don't start getting longer and more webs, although the box isn't big enough to show that in this simulation. You just get the existing webs to continue on. And that's because we've discovered that the expansion rate of the universe is increasing with time, and it cuts off the development of the galaxies. And so that all the structure, we went through this period where the universe formed structure, and then it started to pick up speed and it cuts off the formation of larger structure. And we just get the continued development of the existing structures that we have today. And so we have a picture where we can start with the observations, just extrapolate forward, and we start producing the simulations we see, and now we compare those simulations with the observations we have and find that we have agreement at a quite good level. We're trying to push that agreement down to the 1% level. We're at the few percent level right now. Okay, so we have this model of the universe. We'll come to the answer here of why there's so many galaxies. The reason is there are quantum fluctuations. And we have this accelerating period of expansion of the universe that makes the universe be expanding at a very rapid rate. That takes the things that were in the early universe and stretches them out, things that were smaller than an atom, and stretches them to eventually be as large as galaxies. And then the expansion cools the universe. It goes through a transition where ordinary matter and radiation dominate. You then get the formation of the last scattering surface, a long period until the first stars and galaxies can form. So they're the dark ages of the universe. Then you get the first generation of stars and proto-galaxies, and they develop over time, merging until you started getting modern galaxies. In the meantime, the universe, instead of slowing down the way it's been doing for half of its history, now it's been picking up speed. So that's the mystery of why did the universe suddenly come into this phase where it's picking up speed. It's a good thing, because if you extrapolate back, you find the universe is too young to create everything we had. We needed the extra time compared to what we see for the expansion rate of the universe. But it could have been going more slowly now, and then it would have been okay, because we would have extrapolated back further. So we've got this dark energy, or this accelerated expansion. We have to understand about here is when our solar system started forming. These are the kind of things that we're able to predict with quite great accuracy now. And so the Big Bang's well established. I get to have dinner with princesses, right? And a very nice dinner too, right? That's the king there. And but now we have a whole set of new questions that we're now able to ask. That is, here's the stuff we know about, 0.5% that's stars and visible and gas. But there's a whole bunch of stuff, 3.5%, that's sort of hidden from us. We think must be an intergalactic gas or a galactic gas that's hidden. Then 23% of the universe is made of dark matter, and 73% is dark energy. So we need to know how inflation happened. What's the dark energy? What's the dark matter? You know, what about these other things? There's a whole bunch of other questions we now have. Because we can do the calculations. We put in the simplest model and do the calculations. We reproduce the universe probably to 1% right now. How come? When do these simple models work? We need these new physics, these new substances in the universe. We have to find them and understand them. But we can calculate already. We can make phenomenological models, and they work great. It's like the ideal gas law. We can predict PV equals nRT. That was learned phenomenologically. Later on, StatMech told us it's the random motion, and we unified temperature with energy, the degrees of freedom and so forth. We need to make that step forward in cosmology now. So I had one more. I have about 5 more minutes, or how much time? Okay, good. I had one more point that I really wanted to make, if I can get my stuff to work. So there's this, on the dollar, there's this thing that, on the US dollar, there's this thing that just shows this little pyramid with an eye on top of it. Well, that turns out that's only 0.5% of everything. There's a whole bunch of stuff they aren't showing you. The dark energy, the dark matter, and all the invisible atoms, right? That was the point of this one. So what we're now looking for is the connection between the microphysics of what's going on and the macrophysics of what's happening, just like the ideal gas law. We have the molecules banging around, we can calculate what they happen statistically, and we can derive the macroscopic behavior, the ideal gas law, the expansion of gases with temperature or change in pressure and so forth. We need to do that for the universe as a whole, but one of the things I want to do is this joke that I used on Valentine's Day, but I thought it was so good I'd use it again even though it's not. And so at this ice cream shop, a physicist comes in at the end of every week, every Friday. He comes and sits the second to the last seat, and he talks to the empty seat next to him, offering to buy ice cream, right? And the seat never responds, right? And so the owner is used to the weird people from universities, right? You guys will identify with this. And doesn't say anything, just keeps quiet. But on Valentine's Day, so this is a joke I did on Valentine's Day, he comes in and he makes a really heart-wrenching plea, right? He's really pleading with this empty seat next to him to please accept the so forth. And so the person tending the shop, has to ask, right? He says, sorry. He says, well, let me explain to you. He says, in quantum mechanics, there is the possibility, the vacuum has all kinds of quantum mechanical fluctuations going in it. There is a possibility that a beautiful, intelligent woman who likes and appreciates me will spontaneously appear on the stool next to me and will accept my offer to buy her ice cream, and there is a finite probability that will happen, right? And so the owner raises his eyebrows and says, that's interesting. But, couldn't you just ask one of the girls that comes in here every Friday if she wants some? He says, well, what are the chances of that happening, right? Well, that's not what I'm focusing on. I'm focusing on the fact that it is possible that quantum mechanical fluctuations that are virtual, that are in the vacuum, can be made real. And this is going to be the answer to one of the questions I asked you at the beginning, so take notes. And that is, these pictures, these are quantum mechanical fluctuations that once were in the universe much smaller than the atom. If you take a volume in the universe much smaller than an atom, you will still have billions of quantum mechanical fluctuations that can become real. If the universe expands fast enough, they will be made to pop into reality, right? Maybe not the pretty girl, but the quantum mechanical fluctuations. And one of them is our galaxy. And one of them is the Virgo cluster of galaxies, right? Depending on how big the quantum fluctuation was in physical extent, not amplitude, because one of the things we can see is the amplitude is pretty much independent of scale. It's the when and the how and the expansion of the universe. And so the reason that I have 100 billion galaxies in the visible universe was the visible universe was once so small that there were 100 billion quantum fluctuations in it, and they have survived, right? I've connected the microscopic to the macroscopic in an incredibly tight and useful way. And once I have that, I can actually start thinking about a quantum fluctuation and watch how it evolves. And I see, suppressing one dimension so that there's two, I see that when I release it, when I release it at the beginning of the universe, there's a center part that stays fixed, that's the dark matter, and there's a spherical part that goes out, a spherical shell that goes out, that's the radiation pushing the matter out. That is, if you put a galaxy in there. Now, it's not quite